Okay, so for part 1 of homework 4-4, question 1. If a force acts perpendicular to an object's direction of the motion, that force cannot cause a change in the kinetic energy. Well, the big concept here, right, if the force is acting perpendicular to the motion, so if I've got the force going this way, perpendicular to the displacement or the velocity, then I know that that force would not be doing any work, right? I know the work would be 0 because those two are perpendicular. And so since work relates to my change in energy, if the work is 0, then my change in energy, the change in kinetic energy, would be 0 as well, right? So if the force is perpendicular, the force cannot cause a change in the object's kinetic energy. That is true. The work has to be in the same direction, right, as the displacement in order to change the energy. So hopefully the first question is pretty easy. Question 2 here has two different parts, each with multiple choices, so part A and part B. 3 cars they give us, they have different masses, so car F is the most massive, H is the least, and then G would be in between. All 3 cars have identical tires, indicating that they would all have the same coefficient of friction. So they're all moving at the same velocity when the driver suddenly slams on the brakes. Which car travels the longest distance as it skids to a stop? Well, the key here is to, again, think in terms of energy. When each car is stopping, it stops because eventually the kinetic energy that it has is taken away by the work done by friction, right? So eventually if I did the kinetic energy minus the work done by friction, it would end up with 0 joules of energy. It would end up with no energy. So in other words, my kinetic energy would equal the work done by friction, right? That's why each car stops. Now if we just think here, which is going to help us with part B, it's probably our intuition to say, well, the more massive one's going to have more kinetic energy. But if I actually break this up for part A, which one travels the furthest distance? Well, the kinetic energy we know is 1/2 mass times velocity squared, right? Yes, they do have different masses, but they do have the same velocity. But how do we find the work done by friction? Well, the work done by friction is friction times the distance, right? And how do we calculate friction? Well, we calculate friction as the coefficient, which is the same, times the mass of each car, times gravity, times, again, the distance here for my work, right? So the coefficient of friction times mass times gravity gives me my force of friction, and then my distance. Well, the important part about that, the important part about breaking this up all the way, it's clear to see now that the mass is independent, right? The mass actually cancels out in this calculation, and therefore they have the same velocity, they have the same coefficient, they have the same acceleration due to gravity, they're going to travel the same distance in stopping. So all 3 vehicles, even though they do have different energies, all 3 vehicles would travel the same distance in stopping, because the more mass, the stronger the force of friction is as well. So then for part B, for which car does the friction do the largest amount of work in stopping the car? Well, that one is not going to be the same for each one. And the reason for that is the work is really either half of this equation, right? And so when I'm actually calculating the actual work, the mass is important for finding the work, right? I know the work again would be my force of friction times my distance, or my change in kinetic energy. In either case, the mass is very important for these calculations. So the most work is going to be done on the heaviest car, right? The most massive car. So car F, which has the most mass, that needs the most work done on it because it needs the biggest change in kinetic energy. So good concepts to make sure you're comfortable with. They all travel the same distance, but the most massive car is going to have the most work required in order to stop it. Question 3, you actually could do kinematics for if you wanted to. However, we can also use energies, right? If we've taken the ball and we've thrown it upward, we know that as we throw it, it starts with kinetic energy. At the highest point, it has potential energy, right? So if I use that relationship, I know, again, all of that kinetic energy it leaves with is becoming potential. So I've got kinetic energy equals the potential energy, and then 1/2 mass times velocity squared equals mass times gravity times height. So the mass obviously doesn't matter. So the question becomes, if I double the velocity, what does that do in terms of the height? Well, if I double the velocity, right, I've got 1/2 and then 2 times velocity, but I'm squaring that number. What does that do to the height? Well, ignore the 1/2 and ignore the gravity because those measurements didn't change. So if I double the velocity, then I'm actually quadrupling the left-hand side of the equation, right? So the height would have to quadruple as well in order to keep that balanced. So option A, it says the ball will go twice as high. That's not true because we are squaring our velocity, right? We're actually quadrupling it. So option B is my correct option. The second ball will go 4 times as high as the first one. And then the balls reach the same height again, not right. at the highest point, it will have twice as much gravitational potential. Well, if they started with the kinetic energy, we'd have 4 times as much kinetic energy. So we'd have 4 times as much potential energy. So option D is not right. And then at their highest point, the acceleration of each ball is instantaneously equal to 0. We know, going back to kinematics, that that is not true, right? If at the highest point the acceleration was 0, the object would just get stuck up there and would never come back down. So anyway, option B is the only correct option for this. Okay, so for question 4, you have 2 different planes. They're both, however, the same height. So one is inclined at 30 degrees, one is inclined at 60 degrees. However, they do ultimately reach the same height here, and then they start at the same ground level. Right, so the total height for both of them is the same, and that is very important for us. They do also tell us that there's friction involved. So there's a coefficient of friction, and it's the same for both cases. So the coefficient of friction is the same for both cases. But anyway, they ask us which of the blocks is going to be moving faster when it reaches the bottom of its respective incline. Well, the right answer here, and hopefully most of us were able to work through this without too much trouble, but the right answer is block 2, right? Block 2 will be going faster. Now, in the absence of friction, they would both reach the same speed when they reach the bottom, right? Because by the time that they've gone down, they've lost the same amount of potential energy, and all of that potential energy would have gone to kinetic. However, with friction present, we've got to change our thinking a little bit. So since there's friction involved, we know that we start with a certain amount of potential energy, and they start with the same amount of potential energy, but then they lose some of their energy due to the work done by friction. Right, so their final kinetic energy and their final velocity would be based on how much energy they lose due to friction. Right, what's the work done by friction? Well, when I consider these 2 situations, there's 2 things that make the lower incline ramp worse in terms of friction. One is the fact that if I look at the normal force, because it's a less steep angle, the normal force, the cosine component, would be higher than if it was a steeper angle, right? The cosine component of 60 degrees is not as big as the cosine of 30 degrees. So that tells me that the force of friction is going to be much higher over here than it is over here, the force of friction being lower over here. The other thing that works against us is that when we calculate the work done by friction, we need both the force and the distance, right? Well, the lower grade the slope, the longer the distance it's going to have to travel. So this one goes a much longer distance, right, than this one, which just goes at the 60-degree angle. So it's really twofold here. I have a higher force of friction, and it's acting over a larger distance, so the work done by friction in the 30-degree ramp is going to be way higher than the work done by friction in the 60-degree ramp. So anyway, hopefully this question wasn't too bad. Probably most of us got down to that, but do make sure you pretty thoroughly understand exactly why it's option D. Okay, so question 5 here. Which, if any, of the following statements concerning the work done by a conservative force is not true? So a conservative force is any force that preserves or conserves the energy, right? So for a conservative force, we know that the initial energy would be equal to the final energy. We're looking for which statement is not true. So option A, it can always be expressed as the difference between the initial and final values of the potential energy function. That is true, right? It can always be expressed. That is definitely true, because if I look at the initial and final values of the potential energy, I can find the amount of work done by that conservative force, right? So for example, the work done by gravity as I lift something up would be simply the change in their final potential energies, right? So that's a true statement. So B, it is independent of the path of the body and depends only on the starting and ending points. Once again, that is also true. If I take an object here and I move it straight up, I've given it a certain amount of potential energy. Or if I take it and move it all over the place and do whatever I want, as long as I end up here, I've still done the same total amount of work, the same total amount of energy. So that's true. And then C, when the starting and ending points are the same, the total work done is 0. Well, that's true as well, right? Again, if you were to go around in a circle or do whatever path you may want, if you ended right back where you started, then because it's a conservative force, the net work would be 0, right? If it was a non-conservative force, we would have lost energy along the way due to friction. But if it's a conservative force, the net work would be 0. So all 3 of those are true. So the first 3 are true, so then D, all of the above statements, is true as well. So if you're actually being technical, which of the following statements is not true, then I guess you could make the argument E. You could say none of the above statements are true. This statement itself would be false because all of the above statements are true. But really what they wanted us to answer was D. So my nonsense aside, right, all of these above statements, A, B, and C, are all true. So none of those are not true. Anyway, hopefully this question wasn't too bad. Okay, so question 6 here is definitely a good one to get comfortable with. So they give us two potential energy functions, right? And then they ask us, how do the forces of the systems compare? Well, the important thing here is if they give me a potential energy in terms of x, so they define my potential energy with respect to x. Well, think about going the other direction first. If I give you the force versus the displacement, right? If I give you some function for that, we know the area underneath the curve would represent the work or the potential energy. So the integral of the force, right, if I integrate the force, it's something we've seen before, then that would be my potential energy. So then going from the potential energy to the force is the opposite direction. If I do the derivative of the potential energy function, that gives me the force. So in order to determine the forces on both of these two systems, I want to find the derivative of both of those with respect to x. Well, if I look at each of those functions, right, u sub 1 here equals cx squared plus bx to the third. If I do the derivative of that, right, so the derivative would be the force, it would be 2cx plus 3bx to the second. So I end up with that function. Well, if I look at my other function, right, if I look at my second function there, same type of thing. So the u2 function, the second potential energy function, not the band, is this. When I do the derivative, that constant term just cancels out, right? So I end up getting the force function for number 2 would also be 2cx plus 3bx squared. So if you look at your two force functions, they end up being the exact same thing. So the force is identical on the two systems. So even though this one had that additional scalar, that additional number added, right, in terms of the force did the exact same thing on either of those two systems. So it is a very good thing to understand the relationship between energy and force, right? The integral of force is energy. The derivative of energy is force. So definitely make sure that's a relationship you're pretty comfortable with. So then question 7, probably the last question I'll get to on this first part of the homework. They give us these two vectors here, and they ask us to find the value of x such that b is perpendicular to a. Well, the key concept here is we know that if the two vectors are perpendicular, then the dot product between the two should be equal to 0, right? If two vectors are perpendicular, the dot product should be equal to 0. So to find the dot product, I simply do the dot product by parts here. So I take ax times bx plus ay times by plus az times bz. So I just add all of those up. So ax would be 3 times x here, so it would be 3 times x plus negative 1 times positive 1 plus 4 times negative 5. So I want the sum of all of those to be 0. Well, at this point, it's just pretty easy algebra, right? We end up getting 3x plus negative 1 and 3x minus 1 minus 20 equals 0. So 3x equals positive 21, and x has to be 7. So the only value that makes these two perpendicular, the only value for x that works, is if x equals 7, then these two are perpendicular. So anyway, hopefully you're pretty comfortable with this. If you're not comfortable with the dot product, just make sure you come find me so I can help you get a little bit more practice. Because it's not bad, but it's definitely a skill you need to have down.